Tonight, we embark on a journey to explore the most constant, the most familiar, and yet the most mysterious force in the universe. It is a force that touches you in every second of your existence. It is holding you right now. We are going to tell the story of gravity. Feel the weight of your body pressing down into the mattress. Feel the heaviness of your limbs, the settling of your head against the pillow. We often think of this sensation as tiredness, but it is something far more profound. It is the Earth reaching out to you. It is the planet claiming you, holding you close to its surface, whispering that you belong here. Gravity is the invisible glue of the cosmos. It is the architect of stars, the conductor of galaxies, and the keeper of our atmosphere. Without it, the air would drift away into the vacuum. The oceans would float off the planet. The Earth itself would crumble into dust and scatter into the dark. It is the first force we experience when we are born, and it is the last thing we feel when we lie down to rest. It is the silent background of every life that has ever been lived. And yet, for most of human history, it was a complete mystery. We felt it, but we did not know what it was. Tonight, we will trace the history of this invisible hand. We will travel from the ancient philosophers who thought rocks fell because they wanted to the revolutionary minds who realized that the same force that drops an apple also steers the moon. We will look at the clockwork universe and the mystery that haunted the greatest minds for centuries. How can something touch us without touching us? To understand gravity, we must first understand our place in the void. Imagine the Earth spinning in the silence of space. It is a ball of rock and iron, 12,000 kilometers wide, hurtling around the sun at 100,000 kilometers per hour. Why don't we fall off? Why doesn't the water on the bottom of the world drip into the sky? To the ancients, this was a source of deep confusion. They believed that down was a fixed direction in the universe. They thought the universe had a bottom, and things fell because that was the natural order. But gravity teaches us that there is no fixed down. Down is simply toward the center. To a person in Australia, down is the opposite direction to a person in England. Gravity is a local conversation between matter and the core of the world. It creates a personal horizon for every living thing. Imagine the sheer strength required to hold the oceans in place. The Pacific Ocean contains 700 million cubic kilometers of water. It is heavy beyond comprehension. Yet, gravity holds it to the curve of the Earth so gently that a swimmer can move through it without feeling crushed. It holds the atmosphere, a layer of gas that should by all rights dissipate into the vacuum, in a thin, breathable blue shell. But gravity is also surprisingly weak. Think about this. You can lift your arm. With the simple contraction of a few muscles, powered by the chemical energy of your breakfast, you can defy the gravity of the entire Earth. The whole planet, all 6 sextillion tons of it, is pulling your arm down, and yet you can lift it up. A tiny fridge magnet can pick up a paperclip, winning a tug of war against the entire globe. This paradox, that gravity is strong enough to crush stars but weak enough to be overcome by a magnet, is one of the deepest mysteries of physics. It is the weakest force, but what it lacks in strength, it makes up for in range. It is infinite. The gravity of the Earth does not stop at the atmosphere. It reaches out. It grabs the moon, 400,000 kilometers away, and holds it in a tether. It reaches past the moon, tugging faintly on Mars, on Jupiter, on the distant comets. Every object in the universe is pulling on every other object. You, lying in your bed, are exerting a tiny gravitational pull on the star Betelgeuse. It is negligible, but it is there. We are all connected by this invisible web. Let us travel back to the time before we knew this. Let us go to ancient Greece. The philosopher Aristotle looked at the world and tried to explain why things fall. He did not see a force. He saw desire. Aristotle believed that the universe was made of 4 elements: earth, water, air, and fire. He believed that each element had a natural place. The natural place of earth was the center of the universe, which he thought was the center of our planet. The natural place of water was just above the earth. Air was above water, and fire was at the top. When you picked up a rock, earth, and dropped it, Aristotle said it fell because it wanted to go home. It had an inner longing to return to the center. Smoke, fire, rose because it wanted to return to the heavens. It was a poetic view of the world, filled with purpose and belonging. Aristotle also taught that heavy objects fall faster than light ones. It seems intuitive. A brick falls faster than a feather. For 2,000 years, humanity accepted this as absolute truth. Nobody questioned it. Nobody tested it. The authority of the past was heavier than the rock itself. But then, in the late 16th century, a mathematician in Italy began to ask questions. Galileo Galilei was a man who did not trust authority. He trusted observation. He trusted his eyes. The legend says that Galileo climbed the Leaning Tower of Pisa. He carried 2 spheres, one heavy, made of iron, and one light, made of wood. He leaned over the railing, the wind of the Tuscan landscape blowing his robes, and dropped them both at the same instant. The crowd below watched in amazement. The iron ball and the wooden ball hit the ground at the exact same time. The heavy object did not fall faster. Aristotle was wrong. Whether this specific event happened or not, we know Galileo performed experiments with ramps. He rolled balls down smooth, inclined planes. He slowed down gravity so he could measure it. He used water clocks to time the descent. He discovered something revolutionary. Objects do not fall at a constant speed. They accelerate. They get faster and faster the longer they fall. And, crucially, in the absence of air resistance, all objects accelerate at the exact same rate. This was a profound shift. Gravity was not a desire of the rock. It was a law. It was a force that acted equally on everything. It didn't care if the object was gold or lead. It treated all matter the same. Galileo described the how of falling, but he still didn't know the why. The next leap required a mind that could see beyond the earth. It required Isaac Newton. The year was 1665. The Great Plague was ravaging London. The University of Cambridge closed its doors to prevent the spread of the disease. Newton, a young student of 23, retreated to his family's farm in Woolsthorpe. He spent 18 months in isolation. It was the most productive solitude in the history of science. Newton sat in the orchard, surrounded by the silence of the countryside. He watched the apples ripen on the trees, and, as the famous story goes, he saw one fall. He watched the apple detach from the branch and plummet to the grass. Thud, a straight line down. Then he looked up. Through the branches of the apple tree, he saw the pale ghost of the moon in the daytime sky. And a thought struck him, a thought that would unite the heavens and the earth. He asked, if the earth pulls the apple down, does that pull stop at the top of the tree? Does it stop at the clouds? Or does it reach all the way to the moon? He realized that the moon was not floating, it was falling. Just like the apple, the moon is being pulled toward the center of the earth. But unlike the apple, the moon has sideways motion. It is moving sideways so fast that as it falls toward the earth, it misses. Imagine firing a cannon from the top of a very high mountain. If you fire the cannonball slowly, it arcs down and hits the ground. If you fire it faster, it travels further before curving down. But if you fire it fast enough, at the right velocity, the curve of the cannonball's fall will match the curve of the earth. The ground will curve away beneath it just as fast as the ball falls toward it. The ball will fall forever, never touching the ground. This is what an orbit is. It is a permanent, suspended fall. Newton realized that the force dropping the apple and the force holding the moon were the same force, gravity. He unified the cosmos. Before this, people thought there were two sets of laws, one for the imperfect earth and one for the perfect heavens. Newton showed that there is only one law. The universe is one thing. He retreated to his study, lit by candlelight, and began to work out the mathematics. He invented a new kind of math, calculus, just to describe the motion of changing curves. He formulated the universal law of gravitation. The law was simple and elegant. It stated that every object in the universe attracts every other object. The strength of this attraction depends on two things: mass and distance. The heavier the objects, the stronger the pull. The farther apart they are, the weaker the pull. Specifically, the force drops off with the square of the distance. If you move the moon twice as far away, the gravity becomes 4 times weaker. If you move it 3 times away, it becomes 9 times weaker. This is the inverse square law. It is the geometry of spreading out. Think of butter being spread on toast. The more toast you cover, the thinner the butter gets. Gravity spreads out from a planet into space, getting thinner and weaker, but never disappearing completely. With this law, Newton could predict the motions of the solar system with clockwork precision. He could explain why planets moved in ellipses, not circles. He could predict the tides, showing how the moon drags the oceans around the earth like a watery bulge. It was a triumph of reason. The universe was no longer a place of whimsical gods pushing planets around. It was a machine, a giant, predictable, majestic clock. If you knew the position and speed of every object and the mass of every object, you could predict the future forever. This vision of the clockwork universe dominated science for 200 years. It gave humanity a sense of control and understanding. We could navigate the seas using the stars because we knew where the stars would be. We could predict eclipses to the minute. But there was a problem. A deep, unsettling ghost in Newton's machine. Newton could describe how gravity worked. He could give you the equation, but he could not tell you what it was. How does the Earth pull the moon across thousands of miles of empty space? There is no rope. There are no gears. There is nothing touching. It is a vacuum. This is the problem of action at a distance. How can an object affect another object without touching it? It smelled of magic. It smelled of the occult. Even Newton was disturbed by it. He wrote, that one body may act upon another at a distance through a vacuum is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He essentially said, "I have the math, but I don't have the mechanism. I frame no hypotheses." He accepted the mystery because the math worked so well. And for centuries, it worked perfectly. We discovered new planets using Newton's math. When astronomers looked at the planet Uranus, they noticed it was wobbling. Its orbit wasn't quite right. It was being pulled by something unseen. They used Newton's equations to calculate where this invisible pull was coming from. They pointed their telescopes at the blank spot in the sky, and there, drifting in the dark, was Neptune. They found a world using nothing but a pen and the law of gravity. It seemed that the story of gravity was complete. We had solved the puzzle. We lived in a Newtonian universe, stable and predictable. But nature loves a flaw. There was one tiny, annoying detail that Newton couldn't explain. It was the planet Mercury. Mercury is the closest planet to the Sun. It orbits in a furious hot loop, and its orbit is shifting. The point where it is closest to the Sun, the perihelion, moves slightly each year. It precesses. Astronomers tried to calculate this shift using Newton's laws. They added up the gravity of Jupiter, Saturn, Earth. They accounted for everything, but the numbers didn't match. Mercury was moving slightly too fast. It was a tiny error, 43 arc-seconds per century, a blink of an eye. But in a clockwork universe, even a tiny error is a catastrophe. It meant the gears were slipping. It meant the law was not absolute. Some scientists thought there must be a hidden planet inside Mercury's orbit pulling on it. They named it Vulcan. They spent decades looking for it during solar eclipses, hoping to save Newton's theory. They never found it. Vulcan did not exist. The problem was not a missing planet. The problem was gravity itself. Newton's gravity was an invisible force acting instantly across space. But the universe is not instantaneous. To solve the mystery of Mercury, and to solve the mystery of action at a distance, humanity needed a new way of seeing. We needed to stop looking at objects and start looking at the space between them. We needed to realize that space is not nothing. Space is something. In the next chapter, we will meet the man who saw this something. We will move from the apple orchard of Woolsthorpe to a patent office in Bern. We will meet Albert Einstein. We will see how he tore down the clockwork universe and replaced it with a trampoline. We will learn that gravity is not a force at all, but a curvature, a bending of the fabric of reality. We will see how matter tells space how to curve, and how space tells matter how to move. But for now, return to the feeling of weight, the heaviness in your limbs. It is not just the earth pulling you, it is you pulling the earth. You are locked in an embrace with the planet, a relationship defined by your mass and your distance. You are an anchor. You are part of the gravity of the world. The bed holds you up, pushing back against the pull. You are suspended in the balance between falling and floating. Listen to the quiet of the room. The air molecules are held down by gravity. The walls are held down. The moon outside the window is held in its fall. Everything is connected by this silent desire to be together. The universe wants to collapse into a hug. Gravity is that longing. Drift in that connection. feel the security of being held by a planet that will not let you go. We left the apple orchard of Woolsthorpe with a mystery. Isaac Newton had given us the law of gravity, but he could not give us the mechanism. He told us how the planets moved, but he could not tell us why they felt each other's presence across the freezing vacuum of space. For 200 years, science stood on this precipice, unable to see what lay beneath the equations. To solve this riddle, to see the invisible strings that bind the moon to the earth, we must leave the quiet English countryside. We must travel forward in time to the year 1905. We enter a small, cluttered office in Bern, Switzerland. The air smells of tobacco smoke and old paper. A young man sits at a desk, reviewing patent applications for electric clocks and gravel separators. His name is Albert Einstein. He is 26 years old. He is not a professor. He is not famous. He is a clerk. But inside his mind, the universe is being taken apart and reassembled. While he stamps documents, he is riding beams of light through the cosmos. He is asking questions that no one else thinks to ask. Einstein had already shattered our understanding of time. He had realized that time is not a steady drumbeat heard everywhere at once. He found that time is personal. It slows down when you move fast. He found that space acts the same way. It shrinks when you move fast. He fused these two concepts into a single, four-dimensional fabric, spacetime. But there was a problem. His new theory, special relativity, only worked for things moving in straight lines at constant speeds. It didn't account for acceleration. And, most importantly, it didn't account for gravity. In Einstein's new world of flexible time, Newton's gravity didn't fit. Newton said gravity acted instantly. If the sun disappeared right now, Newton's math said the Earth would fly out of its orbit immediately. But Einstein knew that nothing travels faster than light, not even gravity. If the sun disappeared, we shouldn't know about it for 8 minutes. There had to be a delay. There had to be a wave. There had to be a mechanism. For 10 years, Einstein wrestled with this. He called it his struggle in the dark. He ignored his family. He stopped eating. He paced his room until the floorboards wore thin. He was trying to marry the force of gravity to the geometry of space. The breakthrough came to him in a vision. He later called it the happiest thought of my life. He imagined a man falling from a roof. It sounds like a grim daydream, but to a physicist, it was a revelation. Einstein realized that as the man falls, he does not feel his own weight. If he dropped a set of keys while falling, they would float next to him. In that moment of freefall, gravity seems to disappear. He realized that there is no difference between floating in deep space and falling freely in a gravitational field. The experience is identical. And conversely, there is no difference between standing on Earth feeling gravity and standing in a rocket ship accelerating through space. If you were in a closed room without windows and you felt your feet pressed to the floor, you would have no way of knowing if that pressure was caused by the planet pulling you down or by a rocket engine pushing the floor up into you. Gravity and acceleration are the same thing. This was the equivalence principle. This insight was the key. It meant that gravity wasn't a magical force reaching out across space. It was a property of motion. It was a property of the path you take through the universe. Einstein realized that we are not being pulled by the Earth. We are being pushed. Or rather, we are trying to move in a straight line through space-time, but the space-time itself is curved, and the Earth's surface is getting in our way. This led to the most radical idea in the history of science, general relativity. Einstein proposed that space is not empty emptiness. It is not just a container where things happen. It is a fabric. It is a physical thing. It can stretch. It can twist. It can bend. And what bends it? Mass. Imagine a mattress. It is flat and smooth. Now, place a heavy bowling ball in the center. The mattress sinks. It curves downward around the ball. This creates a valley, a depression in the fabric. Now, take a marble and roll it across the mattress. If you roll it in a straight line, it won't stay straight. As it approaches the bowling ball, it will curve into the dip. It will circle the ball. It might even spiral down and hit it. To the marble, it feels like a force is pulling it toward the ball. But looking from the outside, we can see there is no force. There is no invisible string. The marble is simply following the curve of the mattress. It is trying to go straight, but the surface it travels on is bent. This is gravity. The sun is a bowling ball in the fabric of space-time. It creates a deep gravity well. The Earth is the marble. We are rolling around the curve. We are not being pulled by the sun. We are falling endlessly along the slope of space that the sun has created. John Wheeler, a physicist who came later, summarized it perfectly. Matter tells space how to curve. Space tells matter how to move. It is a cosmic dance. As the Earth moves, the curvature moves with it. The ripples travel. The geometry changes. The universe is not a rigid box. It is a waterbed, constantly undulating with the weight of stars and planets. This explanation solved the mystery of action at a distance. The Earth doesn't need to touch the moon. The Earth touches the space right next to it, bending it. That bent space touches the space next to it. The curvature ripples outward until it reaches the moon, and the moon follows the curve. Gravity is local. It is a contact sport between mass and geometry. But Einstein's theory did more than just explain the mechanism. It made a prediction. It solved the riddle that had plagued astronomers for decades, the orbit of Mercury. Remember the tiny error in Mercury's path? The 43 arc-seconds per century that Newton couldn't explain. Einstein applied his new equations to the problem. He calculated how the massive gravity of the sun would curve space so close to the star. In Newton's world, space is flat. But in Einstein's world, the space near the sun is steep. It is compressed. The geometry of a circle is different there. The ratio of the diameter to the circumference is not pi. It is something else, warped by the mass. When Einstein finished the calculation, his heart pounded in his chest. The numbers matched perfectly. 43 arc-seconds. He had found the missing piece of the puzzle not by finding a new planet, but by redefining the nature of reality. He later said he had palpitations of the heart. He knew in that quiet room that he had unlocked the secret of the cosmos. But explaining Mercury wasn't enough. A scientific theory needs to predict something new, something no one has ever seen before. Einstein realized that if gravity is the curving of space, then it shouldn't just affect rocks and planets. It should affect everything that travels through space, including light. Light has no mass. In Newton's view, gravity shouldn't touch it. But in Einstein's view, light has to follow the road. If the road is curved, the light must curve. He predicted that if a beam of starlight passed close to the sun's gravity would bend it. The star would appear to be in the wrong place. The sun would act like a lens. This was a bold, audacious claim. He was saying that the straightest thing in the universe, a beam of light, could be bent. He was saying we could see around corners. But how could anyone prove it? The sun is blindingly bright. You cannot see stars next to the sun. The glare washes them out. There is only one moment when this experiment is possible. A total solar eclipse, when the moon passes directly in front of the sun, blocking its fire, turning day into night for a few precious minutes. Only then do the stars appear. The world had to wait. World War I broke out. Europe was engulfed in flames. Science was paused. Einstein sat in Berlin, a pacifist in a warring nation, waiting for the clouds of war to clear so someone could look at the clouds of the sky. Finally, in 1919, the war ended. An English astronomer named Arthur Eddington, a Quaker who believed that science should transcend national borders, organized an expedition. He wanted to prove the theory of a German physicist. Eddington traveled to the island of Principe, off the coast of Africa. Another team went to Brazil. They hauled heavy telescopes into the jungle, fighting humidity and mosquitoes. They waited for the eclipse. On the day of the eclipse, it rained. The sky was thick with clouds. Eddington was in despair. But just before totality, the clouds parted. A hole opened in the gray. The moon slid over the sun. The sky turned dark violet. The stars appeared. Eddington frantically took photographs. He was capturing the positions of the Hyades star cluster, which was sitting right behind the sun that day. He needed to see if the stars were where they were supposed to be, or if they had shifted. The eclipse ended. The sun returned. The data was captured on glass photographic plates, but they had to be measured. Months later, back in England, Eddington measured the plates under a microscope. He compared the positions of the stars during the eclipse to their positions at night, months earlier. The stars had moved. The light from the distant cluster had passed through the gravity well of the sun and had been bent. The amount of bending was exactly what Einstein had predicted. Newton's value was wrong. Einstein's was right. Space was curved. When the results were announced at the Royal Society in London, it was pandemonium. It was the death of the old universe and the birth of the new. The headline in the New York Times read, "Lights all askew in the heavens. Men of science more or less agog." Einstein became an overnight celebrity, not because he invented a gadget, but because he changed the shape of the world. He showed us that reality is not a grid of straight lines. It is soft. It is malleable. This realization changed everything. It meant that the universe is dynamic. If space can curve, it can also stretch. It can ripple. It can expand. It opened the door to black holes, regions where space curves so much it rips. It opened the door to the Big Bang, the idea that space itself could expand from a single point. It opened the door to wormholes, tunnels connecting distant points in the fabric. But for all its grandeur, general relativity also explained the mundane. It explained why you feel heavy. When you sit in a chair, you are not feeling a force pulling you down. You are feeling the chair pushing you up. Your body wants to follow the natural curve of space-time. That curve leads towards the center of the Earth. That is the straight line through the warped geometry. you want to fall. Falling is the natural state of motion in a curved universe. But the ground gets in the way. The electrons in the floor push back against the electrons in your shoes. They stop you from following the curve. The sensation of weight is actually the sensation of being accelerated away from your natural path. You are constantly being pushed upward by the earth, intercepting your fall. Gravity is the feeling of the earth getting in your way. This perspective is dizzying. It turns our experience upside down. We are not static objects sitting on a rock. We are travelers trying to slide down a cosmic drain, constantly being caught by the floor. Einstein's theory paints a picture of a universe that is incredibly active. Space is not a stage. It is an actor. It responds to the presence of matter. If you wave your hand, you change the gravitational field of the universe. You send tiny ripples of curvature out into the cosmos. You change the geometry of reality with every movement. Of course, for a hand, these ripples are infinitesimally small. But what if you wave something bigger? What if you wave two black holes around each other? Then the ripples become waves, gravitational waves, tsunamis in the fabric of spacetime. Einstein predicted these too in 1916. But he thought we would never find them. He thought they were too faint, too quiet to ever be heard by human ears. He underestimated us. He underestimated our desire to listen to the song of gravity. In the next chapter, we will jump forward 100 years. We will move from the photographic plates of Eddington to the lasers of the modern era. We will travel to the swamps of Louisiana and the scrublands of Washington State. We will see how humanity built the most sensitive ear in history, LIGO. We will see how we finally learned to listen to the ripples in the fabric. We will hear the sound of two black holes colliding 1 billion years ago. We will hear the chirp that proved Einstein right one last time. We will enter the era of gravitational wave astronomy. But for now, feel the curve. Imagine the bed you lie on is not flat, but a gentle depression in the fabric of the room. Imagine the Earth resting in the depression of the solar system. Imagine the sun rolling around the center of the galaxy. We are all sliding. We are all rolling. We are all falling together through the beautiful bent geometry of the night. We have seen how mass curves space, creating the gravity that holds our feet to the ground and the moon to the sky. We have seen the universe not as a static stage, but as a flexible fabric responding to the presence of matter like a trampoline responding to a heavy stone. But if space is a fabric, then it should do more than just curve. It should ripple. If you drop a stone into a pond, the water does not just dip. It sends waves outward in circles. Albert Einstein saw this possibility in his equations just 1 year after publishing General Relativity. In 1916, he realized that if heavy objects moved violently enough, if they accelerated through the fabric, they should send shutters racing out into the cosmos. He called them gravitational waves. But immediately after predicting them, Einstein doubted they could ever be found. He looked at the math and saw that space is incredibly stiff. It is not like water. It is stiffer than steel. To make it ripple even a tiny amount would require energy on a scale that defies imagination. He calculated that even the Earth spinning around the sun creates ripples, but they are so faint, so infinitesimal, that they vanish almost instantly. He concluded that these waves, while theoretically real, would likely remain forever beyond the reach of human detection. They were ghosts in the math, destined to remain unseen. For decades, the subject was ignored. It was treated as a curiosity, a footnote in the textbooks of relativity. But the universe is far more violent than Einstein knew in 1916. He did not know about black holes. He did not know about neutron stars. He did not know that the cosmos is filled with monsters capable of shaking the very foundations of reality. To understand what a gravitational wave is, we must imagine what it would feel like if one passed through us right now. It is not a wave of heat or light or sound. It is a wave of distortion. As the wave passes, it stretches space in one direction and squeezes it in the other. If a strong enough wave passed through your body, you would literally become taller and thinner for a moment and then shorter and wider an instant later. The distance between your atoms would change. The geometry of your own existence would oscillate. But the waves that reach Earth are not strong. By the time they have traveled across millions of light years, they are whispers. They stretch space by less than the width of a proton. Trying to detect such a movement is like trying to measure the distance to the nearest star, to within the width of a human hair. It seems impossible. Yet the dream of listening to the universe persisted. In the 1960s, a pioneer named Joseph Weber tried to build an ear. He suspended massive cylinders of aluminum in a vacuum, hoping that a passing wave would make the metal ring like a bell. He detected nothing conclusive, but he ignited a spark. He proved that we could try. The torch was passed to a new generation of physicists, Rai Weiss, Kip Thorne, and Ronald Drever. They conceived of a different kind of ear. Not a bar of metal, but a beam of light. They proposed building a machine made of lasers and mirrors, so sensitive that it could measure the heartbeat of the cosmos. They called it LIGO, the Laser Interferometer Gravitational Wave Observatory. The construction of LIGO was a gamble of epic proportions. It required building two massive detectors separated by 3,000 kilometers, one in the swampy forests of Livingston, Louisiana, and the other in the high-scrub desert of Hanford, Washington. Each detector is an L-shaped structure with two arms stretching 4 kilometers long. These arms are concrete tunnels, and inside them are steel tubes pumped out to a near-perfect vacuum. They are the second largest vacuum chambers on Earth, surpassed only by the Large Hadron Collider. The concept is elegantly simple. A laser beam is split in two. Half the light is sent down one arm and half down the other. At the end of each arm, a mirror bounces the light back. When the two beams return to the center, they recombine. If the arms are exactly the same length, the light waves line up perfectly. They cancel each other out, creating darkness. This is called destructive interference. The detector sees nothing. It waits in the dark. But if a gravitational wave passes through the Earth, it will distort the space the detector sits in. It will stretch one arm and squeeze the other. One arm will become slightly longer, the other slightly shorter. Because the distances change, the light takes a different amount of time to travel. When the beams return, they are no longer perfectly aligned. They do not cancel out. Instead, they let a tiny flicker of light through to the detector. That flicker is the signal. That flicker is the wave. The engineering required to achieve this is mind-numbing. The mirrors must be the smoothest surfaces ever created by humans. If the mirror were the size of the Earth, the biggest bump on it would be smaller than a soccer ball. They are suspended on glass fibers to isolate them from the trembling of the ground. The machine is so sensitive that it can feel a truck driving on a highway miles away. It can feel the ocean waves crashing on the distant coast. It can feel the wind blowing against the concrete tunnel. Even the random jitter of the atoms in the mirror, thermal noise, threatens to drown out the signal. For years, the scientists fought this noise. They built active damping systems to cancel out the vibrations of the Earth. They increased the power of the lasers to sharpen the light. They cooled the components. They waited. For decades, LIGO listened to the silence. It heard the noise of the world, the earthquakes, the lightning strikes, the logging trucks, but it heard nothing from the stars. Many began to doubt if it would ever work. Perhaps Einstein was right. Perhaps the waves were just too faint. But while humanity was building its ear, the universe was sending a message. Deep in the cosmos, 1.3 billion years ago, in a galaxy far beyond the reach of our eyes, a dance of death was reaching its climax. Two black holes were locked in a gravitational embrace. These were not ordinary stars. They were the crushed cores of giants. One was 29 times the mass of our Sun. The other was 36 times the mass of our Sun. Each was a sphere of absolute darkness, perhaps only 100 kilometers wide, yet containing the gravity of a stellar system. They had been orbiting each other for millions of years, slowly spiraling closer, losing energy to the very gravitational waves they were creating. But as they drew near, the pace accelerated. The slow waltz became a frantic spin. They whirled around each other at half the speed of light. The space between them was churned into a frenzy. The gravity was so intense that time itself was twisting into knots. And then they touched. In a fraction of a second, less time than it takes to blink, the two black holes merged into one. They coalesced into a single, larger black hole. But there was a cost. The new black hole was lighter than the sum of its parts. 3 times the mass of our Sun had vanished. It had been converted instantly into pure energy, into gravitational waves. The power output of that single moment was greater than the combined light of every star in the observable universe. For that split second, this dark, invisible merger was the brightest event in history. But it shone not in light, but in gravity. A tsunami of distorted space blasted outward in all directions. It traveled through its host galaxy, warping the positions of the stars for a fleeting moment. It left the galaxy and entered the intergalactic void. It traveled for 1.3 billion years. While the wave was traveling, life on Earth was evolving. Single cells became multicellular. Plants colonized the land. Dinosaurs rose and fell. Mammals emerged. Humans learned to use fire, built cities, looked up at the stars, and finally built the machines in Louisiana and Washington. The wave arrived on September 14, 2015. It was early morning in the United States. The detectors had just been upgraded. They were in engineering mode, not fully officially operational yet, but they were on. They were listening. The wave hit the Louisiana detector first. It passed through the concrete, the steel, and the mirrors. It stretched one arm and squeezed the other. The laser light, which had been canceling itself out in darkness, suddenly flickered. 7 milliseconds later, The wave reached Washington. It did the same thing. It shook the mirrors by a distance 1,000th the width of a proton. Computers monitoring the data saw the spike. It wasn't random noise. It was a specific pattern, a chirp. It started low and slow, then ramped up in pitch and volume, ending in a sudden silence. This pattern matched exactly what Einstein's equations predicted for the merger of two black holes. The low hum was the inspiral. The rising pitch was the collision. The silence was the ring down, as the new black hole settled into a perfect sphere. When the scientists saw the data, they couldn't believe it. It was too perfect. They thought it might be a test, a blind injection designed to keep them on their toes. But it wasn't a test. It was the universe speaking. Humanity had heard its first gravitational wave. The implications of this moment were profound. For all of human history, we had been exploring the universe with our eyes. We looked at light, first visible light, then radio waves, X-rays, and gamma rays. But all of these are forms of electromagnetic radiation. They are easily blocked. Dust clouds can hide stars. The core of a galaxy can be obscured. But gravity cannot be blocked. It passes through everything. It passes through the Earth, through the sun, through the densest clouds of dust. It carries information from the deepest, darkest places where light cannot go. We had been deaf for our entire existence. Now we could hear. We had added a new sense to the human species. We could listen to the dark. Since that first detection, LIGO and its sister observatory Virgo in Italy have heard dozens more. They have heard black holes colliding. They have heard neutron stars crashing together. In 2017, they heard a new sound. It was the collision of two neutron stars, the ultra-dense cores of dead suns. But this time, telescopes on the ground saw it too. They saw a flash of light in a distant galaxy at the exact same moment the gravitational wave arrived. This was the multi-messenger moment. We saw the lightning, and we heard the thunder. That single event solved mysteries that had puzzled us for decades. The light from the collision revealed the signature of heavy elements, gold and platinum. We learned that the gold in our wedding rings was not made in normal supernova, but in the violent collisions of neutron stars, announced to us by the shivering of spacetime. The discovery of gravitational waves confirmed the strangest part of Einstein's theory, that space is not a stage but a player. It shakes, it rings, it carries energy. It also gave us a new way to measure the universe. By listening to how loud the chirp is, we can tell exactly how far away the collision was. It is a standard siren, a new way to measure the scale of the cosmos. But perhaps the most beautiful thing about gravitational waves is what they tell us about connection. When you stand outside and look at the stars, you feel small. You feel separated from the vastness by the cold vacuum. But gravity says otherwise. Gravity says you are touching everything. The wave that passed through the Earth in 2015 didn't just move the mirrors in LIGO. It moved you. It stretched your body and squeezed it. It vibrated the atoms in your blood. Every time a black hole collides anywhere in the universe, you ripple. Every time a star explodes, you tremble. We are not observers standing apart from the cosmos. We are woven into its fabric. We oscillate with its history. The silence of space is not silent. It is filled with the hum of collisions, the ringing of black holes, the background rumble of the Big Bang itself. We just needed to build a machine quiet enough to hear it. This new era of astronomy is just beginning. We are building bigger detectors. We are planning to put detectors in space. LISA, the Laser Interferometer Space Antenna, which will consist of 3 satellites flying millions of kilometers apart, linked by lasers. LISA will be able to hear the deep, slow rumbles of supermassive black holes merging in the centers of galaxies. It will hear the universe breathing on the largest scales. We are mapping the dark side of the universe. We are listening to the invisible. And with every new chirp, every new signal from the dark, we learn more about the fundamental nature of reality. But gravity has more secrets to tell. It does not just wave, it lenses. It bends light, acting as a telescope of its own. In the next chapter, we will explore gravitational lensing. We will see how massive clusters of galaxies warp the space around them so profoundly that they magnify the light of objects behind them. We will see how nature builds its own magnifying glasses, allowing us to see back to the very first stars. We will look at the Einstein cross and the arcs of giants. We will see how gravity allows us to see the unseeable. We will also encounter the biggest mystery of all. When we look at how galaxies spin and how light bends, the numbers don't add up. There is too much gravity. There is not enough matter to explain it. We will meet the ghost in the galaxy. We will meet dark matter. For now, imagine the space around you shimmering. Imagine the air, the walls, the ground all gently rippling with the echoes of distant cataclysms. You are not static. You are riding the waves of space-time, bobbing like a boat on an invisible sea. The universe is singing to you. And finally, after 1 billion years, we have learned how to listen. We have learned to listen to the universe through the trembling of space-time. We have heard the collision of black holes ringing like bells in the dark. But gravity does not just speak in waves. It also acts as a lens. It has the power to bend light, to magnify the distant, and to reveal the invisible structure of the cosmos. To understand this, imagine looking through the stem of a wine glass at a candle flame. The flame is distorted. It is stretched into arcs. It is doubled. It is magnified. The glass bends the light passing through it. Albert Einstein realized that gravity does exactly the same thing. Mass acts like glass. When light from a very distant star travels toward Earth, it must pass through the gravitational fields of all the objects in its path. If it passes near a massive galaxy cluster, a swarm of thousands of galaxies held together by gravity, the space around that cluster is curved. It acts as a giant cosmic magnifying glass. The light follows the curve. It bends around the cluster. By the time it reaches our telescopes, it has been distorted. We see the distant star not as a point, but as a smear. We see arcs of light. We see Einstein rings, perfect circles of light, where a background galaxy has been warped around a foreground object. This phenomenon is called gravitational lensing. It is one of the most beautiful sights in astronomy. When we look at deep field images from the Hubble or James Webb Space Telescopes, we see these strange, curved streaks of light scattered among the galaxies. They look like scratches on a lens, but they are actually galaxies far behind the cluster, warped by the gravity in front of them. But this distortion is not a nuisance. It is a gift. The gravity of the cluster acts as a natural telescope, far larger and more powerful than anything humans could ever build. It magnifies the light of the background objects making them brighter and larger. Because of this, we can see objects that would otherwise be invisible. We can see the very first galaxies that formed in the universe, just a few 100 million years after the Big Bang. We are using the gravity of the present to unlock the secrets of the deep past. We are peering through a keyhole made of warped space. Sometimes the alignment is so perfect that we see the same object 4 times. This is the Einstein cross. The light from a distant quasar takes 4 different paths around a galaxy in the foreground, arriving at our eye as 4 distinct points of light arranged in a cross. It is a mirage, a trick of geometry, proving that light is a traveler that must follow the road laid down by gravity. But gravitational lensing revealed something else, something troubling. When astronomers measured how much the light was bending, they could calculate how much mass was in the cluster. To bend light that much, you need a lot of gravity. And to have a lot of gravity, you need a lot of matter. They counted the stars in the cluster. They added up the mass of the gas clouds. They summed up everything that glows. And they found a discrepancy, a massive one. The visible matter, the stars, the gas, the dust, accounted for only a tiny fraction of the gravity needed to bend the light. It was off by a factor of 5 or 6. There was something else there. Something massive, heavy, and completely invisible. It was not interacting with light. It didn't shine, it didn't reflect, it didn't absorb. It was a ghost. This mystery deepened when we looked at how galaxies spin. In the 1970s, an astronomer named Vera Rubin pointed her telescope at the Andromeda Galaxy. She wanted to measure the speed of the stars orbiting the center. According to Newton's laws and common sense, stars on the outer edge of a galaxy should move slower than stars near the center. Think of the solar system. Mercury whips around the sun in 88 days, while distant Pluto takes 248 years to complete a lazy orbit. The further out you go, the weaker the gravity, so the slower you move. Rubin expected to see the same thing in galaxies. The outer stars should be drifting slowly, but that is not what she found. She found that the stars on the edge were moving just as fast as the stars in the middle. They were flying at incredible speeds, 250 kilometers per second. At those speeds, they should have been flung out into intergalactic space. The visible gravity of the galaxy was not strong enough to hold them. The galaxy should have flown apart like a spinning flywheel that spins too fast. But it didn't. It held together. Rubin realized that there must be an invisible halo of matter surrounding the galaxy, providing the extra gravity to hold the stars in. A vast, spherical cloud of unseen mass that extended far beyond the visible spiral arms. We call this dark matter. It is a placeholder name for our ignorance. We do not know what it is, but we know what it is not. It is not normal matter. It is not made of protons, neutrons, or electrons. If it were, it would interact with light. It would cast a shadow. It would glow when heated. Dark matter does none of these things. It passes through normal matter as if it weren't there. You could be holding a chunk of dark matter in your hand right now, and you wouldn't feel it, see it, or touch it. It would fall right through the Earth. The only way it interacts with the universe is through gravity. It has mass. It pulls. We now believe that dark matter makes up about 27% of the universe. Normal matter, The stuff we can see, the stars, the planets, you, me, the dog, the car, makes up less than 5%. The rest is dark energy, which we will meet later. Think about that. Everything we have ever seen, every star in the night sky, every galaxy in the Hubble Deep Field, is just the foam on the ocean. The ocean itself is invisible. We are the minority. We are the rare, glowing debris floating in a sea of dark particles. Dark matter is the scaffold of the cosmos. Computer simulations show that in the early universe, dark matter clumped together first. It formed a vast, three-dimensional web, the cosmic web. Strands of dark matter stretched across the void, meeting at massive knots. Normal gas, hydrogen and helium, was attracted to these strands. It flowed down the gravitational rivers of dark matter and pooled in the knots. There, it became dense enough to ignite into stars and form galaxies. So galaxies are like lights strung on a dark Christmas tree. Without the dark matter branch to hold them, they would never have formed. We owe our existence to this ghost. It creates the gravity wells that allow the universe to have structure. Without it, the universe would be a thin, uniform soup of particles, with no clumps, no stars, no planets, and no life. But how can we be sure it is real? Could we just be wrong about gravity? Maybe Newton and Einstein were wrong about how gravity works over large distances. Maybe we don't need extra matter. We just need new math. This is a valid question. Some scientists propose modified Newtonian dynamics, MOND, but the universe provided a test case, a smoking gun. It is called the bullet cluster. The bullet cluster is actually two huge clusters of galaxies that have smashed into each other. It is a crime scene of cosmic proportions. When the clusters collided, three things happened. First, the stars passed right through each other. Stars are small and space is big, so they rarely collide. They just kept going, like two swarms of bees flying through each other. Second, the gas clouds, which make up most of the visible mass, crashed. Gas is fluid. When two clouds hit, they create friction. They slowed down, heated up, and got stuck in the middle of the collision zone. We can see this hot gas glowing in X-rays. Third, the dark matter. If dark matter exists, it should behave like the stars. It shouldn't crash. It should keep going. It should separate from the gas. When astronomers used gravitational lensing to map the gravity of the bullet cluster, they found that the gravity was not where the gas was. The gravity was where the stars were, on the outside edges. The visible mass, the gas, was stuck in the middle, but the majority of the gravity had moved on. The gravity had separated from the normal matter. This proved that the source of the gravity was not the gas. It was something else. Something that didn't feel friction, something that carried the bulk of the mass and sailed right through the crash. It proved that dark matter is real. So we live in a galaxy that is embedded in a massive, invisible sphere. The Milky Way is just the bright disk spinning in the center of a much larger dark halo. This halo extends hundreds of thousands of light years into space. It stabilizes the disk. Without the dark matter halo, our galaxy would be unstable. It would buckle and warp. The bar in the center would dissolve. The beautiful spiral arms would unwind. Dark matter is the invisible hand that holds the galaxy in shape. Scientists are hunting for this matter right now. Deep underground, in abandoned gold mines and beneath mountains in Italy, they have built detectors. They are waiting for a particle of dark matter, perhaps a WIMP, weakly interacting massive particle, or an axion, to accidentally bump into an atom of xenon or germanium. They are listening for the whisper of the ghost. So far, they have heard nothing. The silence is deafening. It reminds us of how much we still do not know. We have mapped the continents of the universe, but we do not know what the land is made of. But gravity has one more surprise, one more twist that is even stranger than dark matter. We know that gravity pulls. It attracts. It holds the Earth to the sun and the stars to the galaxy. It is an attractive force. But in the late 1990s, astronomers measuring distant supernova discovered something impossible. They were trying to measure how much the expansion of the universe was slowing down. Everyone assumed it was slowing down. Gravity pulls everything back together. So the expansion that started with the Big Bang should be running out of steam. But the data said the opposite. The expansion is not slowing down, it is speeding up. The galaxies are rushing away from us faster and faster every day. Something is pushing them. Something is overcoming gravity. It acts like anti-gravity, pushing space apart. We call this dark energy, and it makes up 68% of the universe. In the next chapter, we will explore this final frontier. We will look at the Big Rip. We will look at the future of the universe where gravity loses the war. We will see how the galaxies will drift so far apart that the sky will go dark. We will see how the universe will end not with a crunch, but with a whimper. A cold, lonely, eternal expansion. We will explore the idea that empty space itself has energy, the cosmological constant that Einstein added to his equations, then removed, calling it his biggest blunder. It turns out, it was his greatest prediction. For now, picture the invisible. Imagine the room you are in is filled not just with air, but with a ghostly substance that passes through you like light through glass. Imagine the galaxy spinning in the night sky, held together by a vast, dark hand. Imagine the light from distant stars bending and weaving through the heavy, invisible landscape of the cosmos to reach your eye. You are seeing the visible tip of an invisible iceberg. The universe is mostly dark, and in that darkness lies the gravity that holds us all. We have walked through the invisible scaffolding of dark matter. We have seen how it acts as the glue of the cosmos, holding galaxies together against the centrifugal force of their own rotation. We have seen it as the great preserver, the gravity that builds structure out of chaos. But gravity has a rival, a dark twin, and this twin does not want to build. It wants to tear everything apart. To understand this new mystery, we must look at the motion of the universe itself. For thousands of years, humans believed the cosmos was static. The stars were fixed in crystal spheres, eternal and unchanging. Even Isaac Newton, with his laws of gravity, assumed the universe was a stable stage upon which the drama of planetary motion played out. But in the 1920s, an astronomer named Edwin Hubble climbed the peaks of Mount Wilson in California. He pointed the largest telescope in the world at the fuzzy patches of light known as nebulae. At the time, we thought these were clouds inside our own Milky Way. But Hubble realized they were not clouds. They were islands. They were entire galaxies, millions of light years away. And they were moving. When Hubble analyzed their light, he saw that it was stretched. It was red-shifted. Just as the siren of an ambulance drops in pitch as it drives away from you, the light of these galaxies was dropping in frequency. They were rushing away from us. And the further away they were, the faster they were fleeing. This was the discovery of the expanding universe. Space itself was stretching, carrying the galaxies along with it like debris floating on a swelling river. It meant the universe had a beginning, a moment when everything was close together, the Big Bang. But for decades, astronomers assumed that this expansion must be slowing down. It was a matter of common sense. It was a matter of gravity. The universe is full of matter, stars, gas, dark matter, and matter pulls on matter. Gravity is an attractive force. It acts like a brake. Imagine throwing a ball into the air. It rises, but as it rises, the gravity of the Earth pulls it back. The ball slows down, stops, and eventually falls back. Scientists believed the universe was like that ball. The initial kick of the Big Bang sent the galaxies flying apart, but the gravity of all the mass in the cosmos should be pulling them back together. The only question was, is there enough mass to stop the expansion completely and cause a big crunch where everything falls back into a fireball? Or is there just enough mass to slow it down forever, so it coasts into a gentle stop? No one doubted that it was slowing down. Gravity always wins. Then came 1998. Two teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, set out to measure this deceleration. They wanted to see how much gravity had slowed the universe over the last few billion years. To do this, they looked for standard candles. These are objects whose true brightness we know perfectly. Specifically, they looked at type II supernovae. These are exploding white dwarf stars that always detonate with the exact same luminosity. They are cosmic light bulbs of a known wattage. By measuring how bright these explosions appeared on Earth, the astronomers could calculate exactly how far away they were. And by measuring their redshift, they could calculate how fast they were moving. By comparing distance and speed across billions of years, they could map the history of the expansion. They expected to see the curve bending downward. They expected to see the brakes being applied. But when they processed the data, the numbers didn't make sense. They checked their telescopes. They checked their math. They checked the dust in the galaxy. The result remained the same. The distant supernovae were dimmer than they should have been. They were farther away than they should have been. This meant that the universe hadn't slowed down in the past. It had sped up. The expansion wasn't decelerating. It was accelerating. The ball thrown into the air wasn't falling back down. It was shooting upward faster and faster, as if a rocket engine had suddenly ignited. This discovery shook the foundations of physics. It meant that gravity, the force that holds the world together, was losing the war. Something else was out there. Something that acted like anti-gravity. Something that pushed space apart. We call this force dark energy, and just like dark matter, we have no idea what it is, but we know it is powerful. In fact, it is the dominant force in the universe. When we do the accounting of the cosmos, the numbers are humbling. Normal matter, the atoms that make up the stars, the planets, the oceans, your body, every book ever written, every structure ever built, makes up less than 5% of the universe. dark matter makes up about 27%, and dark energy makes up the rest, 68%. Everything we can see, touch, or understand is just the foam on top of a vast, dark ocean. We are the rounding error in the universe's budget. The universe is mostly made of a mysterious energy that wants to tear it apart. But what is it? The leading theory takes us back to Albert Einstein. When Einstein first formulated general relativity, he found that his equations predicted a dynamic universe, one that was either expanding or contracting. But like everyone else at the time, he believed the universe was static. To fix his equations, to stop the universe from collapsing under its own gravity, he added a fudge factor. He introduced a term called lambda, the cosmological constant. It represented a repulsive force inherent in empty space itself. It was a mathematical prop to hold up the sky. When Hubble discovered the expansion, Einstein threw lambda away. He called it his greatest blunder. He thought he had missed the chance to predict the expanding universe. But in 1998, the blunder returned. It turns out Einstein was right, but for the wrong reason. The cosmological constant appears to be real. It suggests that empty space is not empty. It has energy. This is a profound concept. We tend to think of space as nothingness, a void where things happen. But quantum mechanics tells us that the vacuum is alive. It is seething with virtual particles popping in and out of existence. It has a vacuum energy. If dark energy is this vacuum energy, it has a very strange property. Unlike matter, it does not dilute. Think about a box of gas. If you expand the box to double its size, the gas becomes half as dense. The atoms spread out. The gravity of the gas becomes weaker. But dark energy is a property of space itself. If you expand the box, you create more space. And because you have more space, you have more dark energy. The density stays the same, but the total amount of energy grows. This creates a runaway effect. As the universe expands, it creates more space. That new space contains more dark energy. That extra energy pushes the universe apart even faster, which creates even more space, which creates even more energy. It is a feedback loop of expansion. Gravity, which depends on matter, is getting weaker as the galaxies drift apart. But dark energy is staying strong. It is winning the tug of war. It has been winning for about 5 billion years. Before that, the universe was denser and gravity was stronger. But as the universe grew, the balance tipped. We are now living in the era of acceleration. So, what is the fate of a universe dominated by this push? It points toward a lonely future. Right now, we see billions of galaxies, but the space between us and them is stretching. Eventually, the distant galaxies will be pushed away faster than the speed of light. They will cross the cosmic event horizon. Their light will no longer be able to reach us. One by one, the galaxies will blink out. They will fade into the red and then vanish. The night sky will grow empty. In 100 billion years, any civilization living in the Milky Way, which will have merged with Andromeda by then, will look up and see nothing. They will see their own island of stars, bound by its own strong gravity. But beyond that, there will be only darkness. They will have no way of knowing that there was ever a Big Bang. They will have no evidence of the expanding universe. The traces of our history will have been erased by the expansion. they will think they are alone in an eternal, static void. We are living in a privileged time, the only time when the history of the cosmos is readable. But there is a darker possibility, a scenario called the Big Rip. This depends on whether dark energy stays constant or gets stronger. If it stays constant, like Einstein's lambda, the galaxies will move apart, but structures held together by strong gravity, like our solar system, or our bodies, will remain intact. But if dark energy is something called phantom energy, if its density increases over time, then the future is violent. As the repulsive force grows, it will eventually overcome the gravity holding the galaxy together. The Milky Way will be torn apart. The stars will be scattered into the void, lonely wanderers. Then the force will grow strong enough to overcome the gravity of the solar system. The Earth will be ripped away from the sun. The planets will drift off into the cold. Then it will overcome the electromagnetic force holding the Earth together. The planet will explode. Finally, in the last fraction of a second, the force will become infinite. It will overcome the strong nuclear force. Atoms themselves will be torn apart. The electrons will be ripped from the nuclei. The protons and neutrons will be shredded into quarks. The fabric of spacetime itself will fray and snap. Everything in the universe will be torn asunder. This is the Big Rip. It is the ultimate victory of expansion over structure. Most physicists believe the Big Rip is unlikely. The Big Freeze, the lonely, cold, eternal expansion, is the more probable outcome. But the fact that we can calculate the shredding of atoms shows just how powerful this mystery force is. There is a profound irony here. Gravity, the force that gathers, the force that builds stars and planets and allows for life, is a local phenomenon. It works best at short ranges. It is the force of intimacy. Dark energy is the force of isolation. It is the force of the void. It creates distance. It turns neighbors into strangers. The history of the universe is the history of the battle between these two titans. For the first 9 billion years, gravity held the upper hand. It slowed the expansion. It built the galaxies. It created the stage for life. But now, the tide has turned. Dark energy has taken the wheel. The universe is stepping on the gas. We are rushing toward a future where isolation is the norm. This realization has thrown physics into a crisis. Our best theory of the very large, general relativity, works perfectly for gravity. Our best theory of the very small, quantum mechanics, works perfectly for atoms. But when we try to use quantum mechanics to calculate the value of the vacuum energy, dark energy, we get an answer that is wrong, wildly wrong. The theoretical prediction is 10 to the power of 120 times larger than what we observe. It is the worst prediction in the history of science. It means we are missing something fundamental. We do not understand the vacuum. We do not understand the nature of nothingness. Is it possible that gravity acts differently on huge scales? Is it possible that our understanding of time is wrong? Is it possible that there are other dimensions, leaking gravity away? These questions lead us to the final frontier of our story. We have looked at the heavy masses curving space. We have looked at the invisible energy pushing space apart. Now, we must try to unite them. We must look for the theory of everything. A theory that can explain the singularity of the black hole and the moment of the Big Bang. A theory that marries the smooth curves of Einstein with the pixelated jitter of the quantum world. In the next and final chapter, We will walk the edge of this frontier. We will look at string theory and loop quantum gravity. We will ask if gravity is even a fundamental force, or if it is an illusion, an entropic effect like heat. We will look at the idea that space-time is not the stage, but the actor, made of tiny, discrete atoms of space. We will explore the texture of reality itself. For now, let your mind expand. Feel the space in the room. It looks empty, but it is not. It is alive with energy. It is pushing against the walls. It is pushing the galaxies away. The universe is breathing out deeper and deeper into the infinite, and we are floating in the breath, held together by the gentle, stubborn pull of gravity, huddled against the dark. Imagine the Earth, the Sun, the Milky Way all holding hands in the dark, resisting the tide. We are the resistance. We are the structure. We are the island of form in a sea of expansion. Time threes. Rest in the center of that gravity. You are held. You are solid. You are here. We have traveled from the apple orchard where Newton first saw the invisible string, to the warped space-time of Einstein, to the dark frontiers of the expanding universe. We have seen gravity as a force, as a curve, as a wave, and as a lens. But there is one final mountain to climb, one final mystery that keeps the physicists awake at night. We have two maps of reality. One is general relativity, the map of the very large, stars, galaxies, the curvature of the cosmos. It is a theory of smoothness, of stretching fabrics and gentle slopes. The other is quantum mechanics, the map of the very small, atoms, electrons, photons. It is a theory of jaggedness, of sudden jumps, of uncertainty and jitter. Both maps work perfectly in their own domains, but they cannot both be right. When we try to combine them, when we try to calculate the gravity of a single electron, or look at the center of a black hole, the math explodes. It yields answers of infinity. It breaks. This is the crisis of modern physics. Gravity refuses to be quantized. It refuses to play by the rules of the subatomic world. So, in this final chapter, we will walk the edge of the known. We will look for the bridge. We will look for the theory of everything. To understand the conflict, imagine the texture of space. Einstein says space is like a smooth sheet. You can zoom in forever, and it will always be smooth. You can stretch it as much as you want. But quantum mechanics says that if you zoom in far enough, nothing is smooth. Everything is pixelated. Down at the Planck scale, a size so small that a proton looks like a galaxy compared to it, space must be frantic. It must be a boiling foam of energy, creating and destroying itself every fraction of a second. This is quantum foam. How can gravity, which relies on smooth curves, exist in a foam? A curve requires a continuous surface. You cannot curve a pile of gravel. You can only rearrange it. One attempt to solve this is string theory. It is a beautiful, elegant, and terrifyingly complex idea. It suggests that the fundamental particles of the universe, electrons, quarks, photons, are not points. They are tiny, vibrating loops of energy, like the strings on a violin. If you pluck a violin string one way, it makes an A note. If you pluck it another way, it makes a C note. String theory says that if a cosmic string vibrates one way, it looks like an electron. If it vibrates another way, it looks like a photon. And if it vibrates in a specific, closed loop, it looks like a graviton. The graviton is the hypothetical particle of gravity. It is the messenger that carries the force, just as the photon carries light. If string theory is right, gravity is just a specific note in the cosmic symphony. The entire universe is music, but there is a catch. For the math of string theory to work, the strings need room to vibrate. They need more than the 3 dimensions of space and 1 of time that we see. They need 10 dimensions, or 11. Where are these extra dimensions? String theorists say they are compactified. They are curled up so tightly that we cannot see them. Imagine looking at a garden hose from a mile away. It looks like a one-dimensional line. But if you walk up to it, you see it is a tube. It has a second dimension, circumference, curled around it. We are living on the hose, unable to see the tiny loops of the extra dimensions. But gravity can see them. In fact, some theorists believe that gravity is so weak compared to the other forces because it leaks. Magnetism is stuck in our 3 dimensions. Light is stuck, but gravity might be able to flow into the higher dimensions, drifting away into the bulk of the multiverse. We only feel the tiny fraction of the force that remains on our brain, our slice of reality. This is a dizzying thought. It suggests that the gravity holding you to your bed right now is ghosting into realities we can never touch. It connects us to a geometry beyond our comprehension. But string theory is not the only contender. There is a rival, a theory that rejects the extra dimensions and focuses on the fabric itself. It is called loop quantum gravity. This theory suggests that space is not a background stage. It is made of atoms of space. It is woven. Imagine a shirt. From a distance, it looks like a single piece of cloth, but up close, it is made of thousands of individual threads looped together. Loop quantum gravity says that space is a chainmail of loops. There's a smallest possible unit of volume. You cannot divide space infinitely. You eventually hit the bottom. You hit the grain of the universe. In this view, gravity is not a force, and it is not a curve. It is the geometry of how these loops connect. When mass is present, it changes the connectivity of the loops. It tightens the weave. Time, too, becomes granular. Time does not flow, it ticks. The universe advances in discrete steps, rearranging the loops of space like a kaleidoscope, turning. These theories, strings and loops, are trying to build gravity from the bottom up. They are trying to find the microscopic mechanism. But there is a third possibility, a radical idea that turns the whole problem upside down. What if gravity is not fundamental at all? What if it is an illusion? This is the theory of entropic gravity, or emergent gravity. Think about heat. Heat is not a particle. You cannot hold a unit of heat in your hand. Heat is a statistic. It is the average motion of billions of atoms jiggling around. It is an emergent property. It only exists when you have lots of atoms. Some physicists, like Eric Verlinde, argue that gravity is the same. It is not a force field. It is the byproduct of entropy. The universe wants to maximize its entropy, its disorder. When you move 2 massive objects apart, you are reducing the entropy of the space-time between them. You are creating order. The universe hates this. It fights back. It tries to push the objects back together to restore the disorder. That push is what we call gravity. If this is true, then gravity is not a fundamental law of nature. It is a statistical inevitability. It is the universe's tendency to shuffle the deck. It means that the feeling of weight you experience is not a pull from the Earth, but the pressure of the universe trying to maximize its information content. This leads us to the holographic principle, which we touched upon in the black hole story. The idea that the three-dimensional world we see, the depth, the distance, the volume, is a projection of information stored on a distant, two-dimensional surface. If space is a hologram, then gravity is part of the projection. It is a geometric consequence of how the data is processed. Imagine playing a video game. When your character jumps, they fall back down. There is gravity in the game world, but there is no gravity in the computer code. There are no little magnets inside the processor. The gravity is a rule of the simulation. Is our gravity the same? A rule of the projection. It is a thought that makes the solid ground feel less steady, but also more magical. It implies that reality is lighter, more fluid than we ever imagined. We do not yet know which of these answers is right. Maybe none of them. Maybe the truth is stranger still. But the search itself tells us something about who we are. We are creatures of gravity. We evolved in it. Our bones grew strong to fight it. Our hearts pump hard to lift blood against it. Our inner ears are calibrated to detect down with exquisite precision. When astronauts go to space, when they leave gravity behind, the body begins to dissolve. The bones lose calcium. The heart shrinks. The eyes change shape. We are not made for the void. We are made for the weight. We often dream of flying, of escaping. Gravity. We see it as a chain, a burden. But gravity is also an embrace. It is the only reason we have an atmosphere to breathe. It is the only reason the Earth holds on to the liquid water of the oceans. It is the force that gathered the dust to make the Earth in the first place. It is the force that squeezed the hydrogen to light the sun. Gravity is the mother of structure. Without it, the universe would be a cold, thin haze of lonely atoms drifting apart forever. Gravity brings things together. It is the cosmic urge for intimacy. It pulls dust into stars. It pulls stars into galaxies. It pulls galaxies into clusters. It pulls us to the planet. So, as we come to the end of this story, reconsider the feeling of your own weight. Do not think of it as heaviness. Think of it as connection. You are being held. The Earth is reaching up to you, pressing against you, keeping you safe from the emptiness of space. You are anchored, and you are pulling back. Your mass, small as it is pulling on the Earth. You are moving the planet just a tiny bit with your presence. You are in a relationship with the world. Look at the objects in your room. They are all held there by the curvature of spacetime. The walls, the air, the blanket. They are all sliding down the same gravity well, huddled together on this rock, traveling through the night. Gravity is the constant. The winds change, the light fades, the temperature drops, but gravity remains. It was there before you were born, and it will hold you until the end. It is the oldest promise in the universe. I will not let you go. As you close your eyes, surrender to it. Stop fighting the pull. Let the mattress take your weight. Let your muscles relax. Let the curvature of space cradle you. You are riding the Earth as it orbits the sun. The sun orbits the galactic center. The galaxy drifts through the cosmic web. You are part of a great, silent motion, guided by the invisible hand. There is nothing you need to do. The force that moves the stars is taking care of you. Rest in that certainty. Float in the geometry of the night. Thank you for listening to Dreaming Through Knowledge. May your sleep be heavy, your dreams be light, and your orbit be peaceful. Good night.